All right, today we are going to talk about negative feedback op-amp circuits. There are multiple different types of negative feedback op-amp circuits, so we're going to focus on one today. And then our next class meeting will be focused on commonly used negative feedback topologies. One interesting thing about a negative feedback op-amp circuit is that it actually lowers the overall gain of the circuit, thereby extending the linear range. So this is our first op-amp circuit where we should expect the amplifier to actually present us with a scaled version of our input signal. All right, so the circuit that we are going to look at first is this guy. Notice that I have drawn the inverting input terminal on top. And I'm also putting the positive power supply voltage on top. Here I'm going to have my non-inverting input voltage, or excuse me, my inverting input voltage V minus. Here I will have my my non-inverting input voltage V plus. And then out here will be my output node. So this is our generic op-amp. We're going to apply negative feedback by providing a path that connects from the output terminal of the op-amp to the inverting input terminal of the op-amp. I'm going to call this resistance R2. We're going to have a resistance R1 between the inverting input terminal and an input signal. And we're going to have our non-inverting input terminal tied to ground. We are going to wind up working this problem numerically, so I'd like to identify a few key figures here. So for the op-amp itself, let's say that Rn is equal to 1 mega ohm. R out is equal to 100 ohms. And our open loop gain, AVOL, is equal to 10 to the 5 volts per volt. For our feedback network, let's say that R1 is equal to 5 kilo ohms. R2 is equal to 10 kilo ohms. And let's say that our input voltage Vn is 1 volt in this case. We are going to try to find the following quantities. First, our output voltage. Second, our closed loop voltage gain, defined to be the ratio of V out over V in. Our differential voltage VD, which is the voltage present at the non-inverting input terminal minus the voltage present at the inverting input terminal. Then we are going to try to find Rn, where Rn is the resistance seen looking into the input terminal. This is different than the input resistance of the op amp itself because this is including the effects of feedback. And lastly, we're going to try to find R out. This is the resistance seen looking into the output terminal of the system, again, including any effects of feedback. So we are going to analyze this circuit using the practical op amp model. And so, as per usual, the first thing that I will do is draw my practical op amp model, and then I'll make all of our necessary connections. I am going to do something slightly different here. Let's see, so this should be 1 mega ohm. For this particular circuit, and really anytime I have negative feedback, I tend to place the non-inverting input terminal on bottom and the inverting input terminal on top, just to make the circuit easier to draw with our feedback network. So that's going to make our differential voltage VD have positive polarity on bottom, which is opposite what we would usually have. Continuing on. Here's my output resistance of 100 ohms. And then here is my reference node for my op amp circuit. All right. So if we look back, this is our practical op amp model of just the op amp portion itself. If we refer back to our figure, we can see that the non-inverting input node labeled V plus is connected directly to ground. So I'm simply going to place a short circuit here. Between my inverting input node and ground, I have a resistor R1 in series with my input voltage. Where R1 was 5 kilo ohms. And Vn was 1 volt. The only thing I have not yet included is my feedback resistance, which is 10 kilo ohms, and it is connected between my inverting input node and my output node, like so. And lastly, we're going to be taking our output voltage here. So I am going to do is I'm going to strategically apply Kirchhoff's current law at the inverting input node and the output node in order to solve for a few quantities. So at my inverting input node, I'm going to be adding this current, and this current together. At my output node, I'm going to be adding this current and this current together. So let's start at our inverting input node. We're going to have a voltage V minus 1 volt over 5 kilo ohms plus V minus V out over 10 kilo ohms plus V minus minus VD, which is at ground, so V minus minus 0, or V minus over 1 mega ohm is equal to 0. So this is equation 1. When we apply KCL at our output node, we're going to have V out minus 10 to the 5 VD, where in this case, VD is V plus 0 minus V minus, or negative V minus, divided by 100 ohms. And we're also going to have V out minus V minus over 10 kilo ohms is equal to 0. And this is equation 2. If we solve this system, which only has two unknowns, V minus and V out, we find that V minus is equal to 20.199 microvolts. And V out is equal to negative 1.99999392 volts, which is approximately negative 2 volts. So this was part A, and we have completed it. We have determined our output voltage. Okay. Part B, we are asked to find our closed loop gain, where AVCL is our output voltage divided by our input voltage, which is negative 1.99999392 volts, divided by positive 1 volts, gives us a voltage gain of negative 1.9999392 volts per volt, or approximately negative 2 volts per volt. So this is one of the things that negative feedback does. Okay. Negative feedback tends to significantly lower the voltage gain of the amplifier system, right? We had a closed loop gain, or excuse me, an open loop gain of positive 100,000, and we wound up getting a closed loop gain of approximately negative 2. We'll see shortly that this negative 2 parameter comes effectively from the feedback network that was applied. The open loop gain of the system doesn't really play any significant role for the overwhelming majority of negative feedback op-amp circuits. Getting a little bit ahead of myself there. All right, our next thing to determine, part C, was our differential voltage VD, which is always defined as the voltage at the non-inverting input terminal minus the voltage at the inverting input terminal. So that's going to look like 0 volts minus -20.199 microvolts or -20.199 microvolts. This is another thing that we are going to see is characteristic of negative feedback circuits. The differential voltage will always come out to be a very, very small quantity. All right. For part D, we are asked to determine the input voltage, or excuse me, the input resistance for the system as a whole. We are going to use effectively Ohm's law to do this. We are going to say that the input resistance when looking into the input terminal is simply the current observed IN caused by some input voltage VN. So I'm going to scroll back up to our practical model here. Our 1 volt source here is our voltage VN. The current leaving the positive polarity terminal of our 1 volt source is our current IN. So just using Ohm's law, I can say that my current IN is simply 1 volt minus V minus divided by 5 kilo ohms, since I know what the voltage at my inverting input terminal is. Okay. Oops, and I made a mistake here, sorry. Should be the ratio of VN over IN, not the other way around. So this is going to be VN divided by VN minus V minus over our resistor R1. And if I substitute in my numbers here, this is going to look like 1 volt divided by 1 volt minus 20.199 microvolts divided by 5 kilo ohms. And it comes out to be 5,000.100997 ohms, or approximately 5 kilo ohms, which means the input resistance, yes. All right, so let's scroll up here. So the question is, why is it 1 volt minus 20.199 microvolts? So when we solved for V minus, we got positive 20.199 microvolts. Yeah, you're looking at VD probably. Yep. Okay. So we see that the input resistance of the system looks effectively like the resistor R1, and the input resistance of the op amp, capital RN, isn't really having any effect on things. That is because of this particular negative feedback topology. When negative feedback is applied, what typically happens is that our input and output resistances of our amplifier are modified, and the type of negative feedback that we apply determines whether or not those input resistances increase or decrease. In this particular case, we are seeing that the effect of the 1 mega ohm of input resistance of our op amp by itself gets scaled down to a factor of about 0.1 ohms. So we see a dramatic decrease in the resistance of the op amp. All right. The last thing that we need to determine is the output resistance with our feedback parameters included. We are going to approach this by using a Thevenin equivalent resistance seen looking into the output terminal, which would be Thevenin voltage divided by Norton current, where recall that a Thevenin voltage is an open circuit voltage and a Norton current is a short circuit current. Well, we already know what the open circuit voltage at the output is because we've solved for it. Our open circuit voltage at the output is simply V out, negative 1.9999392 volts. For our short circuit current, we are going to have to analyze this circuit again under the constraint that our output terminal is shorted to ground. So I'm going to redraw this circuit. Here's our 1 mega ohm resistance from our op amp, our differential voltage VD, and to the 5 times VD. Our 100 ohms of output resistance for the op amp itself. Here's our output terminal V out. My non-inverting input voltage is still at 0. Inverting terminal, we have that 5 kilo ohm resistor in series with our 1 volt source. And then we have our feedback loop. Now, because we are determining our Norton current, I'm going to short circuit my output node, and we're going to measure or calculate this current, I Norton. So how I'm going to do this is I'm going to say that this current, which depends on VD and therefore in turn depends on the voltage V minus, plus this current, which depends on the voltage V minus, will sum together and form I Norton. To solve for V minus, I'm going to have to apply Kirchhoff's current law at the inverting input node. So KCL at My inverting input node, excuse me, is going to give me V minus 1 volt over 5 kilo ohms plus V minus over 10 kilo ohms. I can say this because my output terminal is connected directly to ground. So that's why I don't have a minus V out term here. Plus V minus over 1 mega ohm is equal to 0. And if I solve this one equation, one unknown system, as it were, we find that our voltage V minus in this case is 0.664445 volts. Now I will apply KCL at our output node. And so I see that my current I Norton is V minus over 10 kilo ohms plus ten to the 5 times negative V minus, since VD is equal to negative V minus, over 100 ohms. And when I substitute in my numerical value for V minus, what I find is that I Norton comes out to be negative 664.45176 amps. Now I do want to point something out here. There are very few op amps that have been designed that would be able to actually carry a current of 665 amps, right? This is a mathematical construct that is allowing us to determine how the system is going to behave. If we actually shorted the output terminal of an op amp to ground, we would likely only see currents in the range of milliamps because that's what they are designed to carry. It would burn out if we put anywhere close to this amount of current. So just want to be very clear about that. So if we substitute in this value for our I Norton, negative 664.45176 amps, we get an output resistance, lowercase r, of 3.0085 milliohms. So in this case, we see that our output resistance, lowercase r, is significantly smaller than our output resistance, uppercase r, by a few orders of magnitude. So again, we see our modification of input and output impedances or resistances. All right, so the math that was involved here was not overwhelming, but it was tedious, okay? So what I would like us to do is to take a look back at what the ideal functionality of an amplifier circuit is, and then use that to come up with some idealized parameters and we're going to reanalyze this circuit using those idealized parameters. So we're going to start by reviewing an idealized generic amplifier characterized by some input resistance Rn, some open loop voltage gain, and some output resistance R out. Like so. And we're going to connect to this amplifier. Let's detail this out real quick. Here is our amplifier. On the left-hand side, we are going to include some sort of source, where I'm choosing to make it a practical source. And on the output or load side, I'm going to choose some resistive load, RL. I'm going to define my load resistance VL as follows. Okay. So on the left, we have our source. In the middle, the amplifier. On the right, the load that the amplifier network is driving. Okay. So the ideal behavior of this type of circuit, as we've previously discussed, would be that VL, our load voltage, is a scaled version of VS, our source voltage. Okay. So now we're going to talk about what values of Rn, R out, and AVOL make that happen. Okay. So if we look at our source voltage, Vs, what we want to have happen is that all of that voltage Vs will be applied across the resistance Rn, effectively saying that there is no voltage drop over the resistance Rs, which is the source's internal resistance. For that to be true, we would need Rn to be infinity, because if Rs isn't carrying any current, then all of the voltage Vs appears at the input terminals of the op amp. So our first idealized parameter is to say that Rn is infinitely large. Okay. Our second idealized parameter will be for R out. So in this case, we want all of the voltage that's being supplied by our dependent source to reach our load. meaning that we want no voltage drop to occur over the resistor R out. Well, we can't replace it with an open circuit here, because if we did that, we would find that none of our voltage being supplied by our dependent source makes it to our load. Instead, we are going to replace R out with a short circuit or a 0 ohm resistance. In doing so, VL is exactly AVOL times VN, where VN is equal to VS when RN is equal to 0. So we have our characteristic that we're looking for. Our load voltage VL is now equal to our open loop gain AVOL times our source voltage VS. Now let's talk about idealizing our gain. So in an ideal amplifier, we want our open loop gain to be as large as possible, or infinity. The reason why we want our open loop gain to be as large as possible is because our closed loop gain will then be determined entirely by our feedback network. So effectively, with a extraordinarily large open loop gain, our feedback network tells us what our fixed gain for our designed system will be. So these are our 3 idealized parameters. And what we are going to do now is reanalyze the circuit that we've been dealing with under these new parameters. So here's my infinity ohm resistor representing my input resistance, voltage V plus, voltage V minus. Here's my voltage VD. Then I have infinity times VD here for my dependent voltage source. I have a 0 ohm resistor here representing the op amp's internal output resistance. Here is my output voltage V out. And my reference. And now I'm going to connect the remainder of my circuit. So we have a short here. A 5 kilo ohm resistor here, which I'm going to call R1. Our 1 volt input voltage here. And our feedback resistance here. R2 is equal to 10 kilo ohms. All right, so, and just to be clear, here's my output voltage VF. All right, so before we actually get into any analysis whatsoever here, we are going to take a look at something, okay? So if we write a Kirchhoff's voltage law equation around this loop. So this is KVL at our output loop. What we find is that infinity times VD is equal to V out. And we can mathematically manipulate this very slightly to say that our differential voltage VD is V out, whatever it may be, divided by infinity, which implies that our differential voltage VD will be 0 volts. This is what's known as our voltage constraint relationship, which can be summarized as the voltage present at our non-inverting input terminal, V plus, must be exactly equal to the voltage present at our inverting input terminal in an ideal op amp, or phrased how you may have heard it before, there can be no potential difference between the input terminals of an ideal operational amplifier. This is where one of our ideal op amp rules comes from. Okay. So with that observation, we can now apply Kirchhoff's current law at our inverting input node. We will actually see our other ideal op amp rule comes from this analysis as well. What I mean specifically here, so KCL at inverting input node is going to give us 1 volt, V minus 1 volt over 5 kilo ohms, or R1, plus V minus V out over 10 kilo ohms, plus V minus over infinity ohms is equal to 0. This bit obviously just goes to 0 amps. We're dividing by infinity again. This is where our second ideal op amp rule comes from. Okay, no current can flow into or out of our input terminals because we have an infinitely large resistance between our input terminals. Okay, so ideal op amp rule regarding voltages comes from our voltage constraint relationship. Our ideal op amp rule regarding currents comes from the fact that we have an infinitely large input impedance. Now, since from our voltage constraint relationship, V minus, our inverting input voltage, has to be identical to V plus, and we can see by inspection here that V plus is 0 or ground. That means V minus is also ground, which means this simplifies to -1 volt over 5 kilo ohms minus V out over 10 kilo ohms is equal to 0. And so I'm just going to do a little bit of algebraic manipulation here. -1 volt over 5 kilo ohms is equal to V out over 10 kiloohms. And finally, we can see that V out is equal to negative 10 kiloohms over 5 kiloohms times 1 volt is equal to negative 2 volts, which is extraordinarily close to what we got using our practical op-amp model. Our voltage gain in this case would be negative 2 volts per volt, where our voltage gain AVCL, we can see by inspection from the math here, is simply negative R2 over R1, was established entirely by our feedback network. And this is a consequence of dealing with an ideal negative feedback op-amp circuit. All right, so the last thing that we're going to talk about today is to rehash our ideal op-amp rules, and then to talk about, yes. Okay, so from our voltage constraint relationship here, V plus is equal to V minus. We can observe that V plus is grounded, so V minus is also 0. Yep. Anything else? All righty. All right. So now we're going to talk about ideal op-amp rules and analysis. My first caveat here is that we can only treat op-amps as ideal under the following conditions. Number one, and this is the most important, we have a negative feedback circuit. Cannot treat our op-amp as ideal for positive feedback circuits or open loop circuits. Only when we have negative feedback do the ideal op-amp rules have a potential to apply. Our second rule is that the actual input resistance of the op-amp from the data sheet, whatever, is large. So typically we would say that Rn is much, much greater than any of our feedback resistances. As long as we're using kilo-ohm size resistors for our feedback network, this is going to be guaranteed. 3, we need R out to be small. So R out should be less than any load resistance or feedback resistance. And number 4, open loop voltage gain needs to be large. It's actually kind of hard to quantify what large is here. In some applications, voltage gain of 10 would be considered large. In other applications, a voltage gain of several thousand would be considered large. So in this case, what we're going to say, our open loop gain is large. So AVOL needs to be significantly larger than our desired closed loop voltage gain if we're doing a design problem. Okay. For the intents and purposes of this class, I will tell you whether or not I want you to use the ideal op amp rules or the practical op amp analysis. Okay. All right. So, yes. AVCL, the closed loop voltage gain. All right, so rule number 1. No current can flow into or out of the input terminals of an ideal op amp. Which we know is because we have an infinitely large input resistance. Rule number 2 comes from our voltage constraint equation. And it says there can be no potential difference between the input terminals of an ideal op amp. This is simply our voltage constraint equation. So I'm just going to put in parentheses here, V plus the voltage present at the non-inverting input non-inverting input terminal must be equal to the voltage present at the inverting input terminal. So these are our rules for how an ideal op amp behaves. Now let's develop a simple procedure for analyzing ideal op amp circuits. So we're going to rework problem that we just dealt with without using the model, but applying these rules, and develop a algorithm or procedure for handling these circuits. We're going to just mark this guy symbolically. So here's our resistor R2. Here is our resistor R1. Here's our input voltage. This guy. All right, so step one is going to be apply rule number one. And determine the voltage V plus, which is the voltage present at the non-inverting input terminal. How I typically do this is I make a note to myself that the current flowing into the op amp in either of the input nodes must be 0. And then I do any circuit analysis that is necessary to determine the voltage V plus. In this case, we can find by inspection that V plus is equal to 0 volts. Step two, to apply rule number two and perform Kirchhoff's current law at the inverting input terminal. So in this case, the application of op amp rule number two tells us that the voltage present at our inverting input terminal is 0 volts. And now we're going to write our KCL equation. So we're going to have 0 minus Vn, so negative Vn over R1 plus 0 minus V out, so negative, sorry, screen moved on me, over R2 equal to 0. And then step three will simply be solve our KCL expression for V out. So if we take our equation, we're going to move the V out over R2 to the right-hand side. So this gives us negative Vn over R1 is equal to V out over R2. And from here, V out is negative R2 over R1 times V. Okay. These are the three steps that we are going to perform when we're analyzing any ideal op amp circuit. Okay. getting slightly ahead of myself, I'm going to identify this circuit. This type of circuit is what's known as an inverting amplifier. The reason why it's called an inverting amplifier is because the sign on the output voltage is opposite the sign on the input voltage. Meaning, if we apply a positive input voltage, we get out a negative output voltage. If we apply a negative input voltage, we get out a positive output voltage. Okay. Another way that we can easily identify that this is an inverting amplifier is because the input signal, Vin, is applied through our feedback network to the inverting input terminal, right? There are two different ways that we can tell that this is an inverting amplifier. We have an input-output relationship. V out is equal to negative R2 over R1 times V in. And from this, we have a closed loop voltage gain, AVCL, defined to be V out over V in of simply negative R2 over R1. These boxes. These are the important parameters that I expect you to be able to effectively recite or regurgitate to me for your exam and all that kind of good stuff. I want you also to notice that for this particular amplifier circuit, we can get amplification, meaning the magnitude of our output signal can be larger than the magnitude of our input signal. But we can also get attenuation, meaning the magnitude of our output signal could be smaller than our input signal. And whether we have amplification or attenuation is purely decided by the ratio of those resistors R2 and R1. So we get a very high degree of functionality in as much as we can set our voltage gain to be whatever we want it to be. The drawback is that we get inversion as well, meaning that the amplitude of our output signal is of the opposite sign of our input signal. All right, that's where we're going to stop for today. We are going to use these this three-step procedure to analyze, I think 5 or 6 more different negative feedback op-amp circuits on Wednesday, and we will develop relationships and discuss their behavior as we go through. We're going to talk about effectively now how the operational amplifier got its name by describing the different types of mathematical operations that can be carried out using a negative feedback op-amp circuit. All right, thank you for your time. If you have any questions, feel free to hit me up.